What if I told you everything we see, every star, every galaxy, even our own bodies, makes up less than 5% of the universe? The rest is an invisible, mysterious force we can't even directly observe. Scientists call it dark energy and dark matter, the missing pieces of our cosmic puzzle. And here's the wild part: we have no idea what they truly are. That's right, 95% of the universe is completely unknown to us. It's like living in a house where you only recognize the furniture in one tiny corner, while the rest remains hidden in shadow. Now imagine standing under a night sky, staring up at those glittering stars. What you're seeing is just the tip of the iceberg. The real story lies in the darkness between them, a vast, invisible ocean of energy that's literally pushing the universe apart. Dark energy isn't just some abstract idea. It's the reason galaxies are speeding away from each other faster and faster, defying gravity itself and dark matter. It's the hidden scaffolding holding galaxies together, an unseen hand shaping everything we observe. But despite decades of research, these cosmic ghosts refuse to give up their secrets. That's where things get exciting, because when science hits a wall, imagination kicks into high gear. Over the years, researchers have proposed some truly mind-bending theories to explain this missing energy, from hidden dimensions and parallel universes to bizarre new particles that rewrite the laws of physics. Some ideas sound like science fiction, others border on philosophy, but all of them share one thing: they challenge everything we think we know about reality. So buckle up, because today we're diving into 30 of the most astonishing theories about the universe's missing energy. From the brilliantly plausible to the wildly speculative, we're about to explore the edges of human understanding, and trust me, you won't want to miss a single one. Let's start with a concept that bends the very definition of empty. Quantum vacuum fluctuations suggest that what we call empty space is anything but. At the tiniest scales, particles and antiparticles spontaneously appear and vanish in a chaotic dance, lasting just fractions of a second before annihilating each other. This isn't some abstract idea. It's been proven through experiments like the Casimir effect, where two metal plates placed incredibly close together in a vacuum experience a faint but measurable force pushing them together. Why? Because the space between the plates limits the types of quantum fluctuations that can occur, while the outside doesn't, creating an imbalance. Now, here's where it gets wild. Some physicists think these fleeting bursts of energy might hold the key to dark energy. According to quantum field theory, every cubic centimeter of so-called empty space crackles with this activity, packed with potential energy. And if you add up all that energy across the vastness of the universe, it eerily aligns with the mysterious force we've labeled dark energy, the very thing accelerating cosmic expansion. But there's a catch. When scientists try to calculate the exact amount of energy these fluctuations should produce, the numbers come out astronomically wrong, like 10 to the power of 120 times too big. That's a 1 followed by 120 zeros. So why hasn't this infinite-seeming energy torn the universe apart already? One possibility is that we're missing a crucial piece of the puzzle. Maybe these fluctuations cancel each other out in ways we don't yet understand, leaving behind just a faint whisper of energy, enough to nudge galaxies apart but not obliterate reality. Others argue that our math itself might be incomplete, like using Newton's laws to describe black holes before Einstein came along. Either way, the quantum vacuum remains one of the most tantalizing leads in the hunt for dark energy, a reminder that sometimes the answers hide in the spaces we assumed were nothing at all. Einstein might have called it his biggest blunder, but sometimes even geniuses underestimate their own ideas. When he first introduced the cosmological constant in 1917, it was a mathematical fudge factor, a way to keep the universe static in his equations, because at the time everyone believed the cosmos was unchanging. Then, when Edwin Hubble discovered the universe was actually expanding, Einstein tossed the idea aside, dismissing it as unnecessary. But here's the twist: decades later, that so-called blunder came roaring back into fashion as one of the leading explanations for dark energy. The cosmological constant suggests something radical: that empty space isn't empty at all. Instead, it's brimming with an intrinsic energy, a kind of background hum that permeates every corner of the universe. Think of it like a stretched rubber sheet that never sags, no matter how much you pull. This energy doesn't dilute as space expands. It stays constant, which means as the universe grows, there's more and more of it. And that's exactly what we see today: galaxies accelerating apart as if pushed by an invisible force. But not everyone's convinced. Critics point out a glaring issue. When theorists calculate how strong this energy should be, the numbers are wildly off. Quantum physics predicts a value that's unimaginably larger than what we observe, so big it should have ripped atoms apart before stars even formed. This mismatch is one of the biggest unsolved problems in physics, nicknamed the worst theoretical prediction in history. Some argue it means we're missing a deeper mechanism, like an unknown symmetry that cancels out most of this energy. Others wonder if the constant isn't really constant at all. Maybe it changes over time or interacts with matter in ways we haven't detected yet. What makes this theory so compelling, despite its flaws, is its eerie simplicity. Unlike exotic new particles or hidden dimensions, the cosmological constant doesn't require rewriting the laws of physics, just accepting that space itself has a stubborn, unchanging energy. And in science, sometimes the simplest ideas are the hardest to kill. Einstein might have abandoned it, but the universe seems to be whispering that he was onto something after all. What if dark energy isn't constant at all? That's the tantalizing idea behind quintessence, a theory proposing that the universe's missing energy might come from an exotic, ever-changing field stretching across space. Unlike the rigid cosmological constant, quintessence behaves more like a living thing, evolving over time and even fluctuating in strength. Picture it like an invisible wind pushing galaxies apart, one that might gust stronger or weaker depending on when and where you measure it. This isn't pure speculation either. Scientists draw a direct line from quintessence to another cosmic mystery: inflation, the explosive expansion of the universe moments after the Big Bang. Both phenomena seem to involve fields that stretch space itself, but while inflation ended long ago, quintessence could still be at work today, gently accelerating the cosmos. The beauty of this theory lies in its flexibility. The cosmological constant faces that infamous wrong by 120 orders of magnitude problem because it's locked into a single, unchanging value. Quintessence sidesteps that by allowing its energy density to shift, perhaps starting high and then tapering off, or even oscillating like an undulating wave. Some models suggest it could interact with dark matter, creating a delicate cosmic dance where the two unseen forces influence each other. Others propose it might one day reverse course, switching from repulsive to attractive, potentially leading to a big crunch scenario where the universe collapses back in on itself. But here's where it gets even stranger. Certain versions of quintessence predict eerie side effects, like regions of space where the field grows so strong it tears atoms apart, a phenomenon called phantom energy. If that sounds apocalyptic, well, it is. In one hypothetical scenario, phantom energy could eventually rip apart galaxies, then stars, and finally even space-time itself in a cataclysmic big rip. Thankfully, observations so far don't point to this extreme version, but the fact that such wild possibilities exist shows just how much we still don't understand. What makes quintessence so compelling is how it mirrors other breakthroughs in physics. Just as Einstein's static universe gave way to Hubble's expanding one, maybe our assumption of a constant dark energy will yield to something more dynamic. After all, nature rarely stays still. Why should the force shaping our cosmos be any different? Phantom energy isn't just another theory, it's a cosmic horror story hiding in the math. Imagine dark energy on steroids growing stronger over time instead of remaining constant. This isn't just about galaxies drifting apart, it's about the fabric of reality itself unraveling. The idea stems from certain versions of quintessence where the field's energy density doesn't just persist, it escalates. Picture stretching a rubber band until it snaps. Now replace the rubber band with space-time, and you've got the essence of the Big Rip. The numbers behind this scenario are chilling. If phantom energy exists, its repulsive force would eventually overpower gravity, electromagnetism, even the nuclear forces holding atoms together. Galaxies would be the first to go, ripped apart as the space between stars expands faster than light can bridge the gap. Next, solar systems would fly apart, planets torn from their orbits. In the final moments, atoms themselves would disintegrate, their nuclei shredded by the unstoppable stretching of space. Even time as we know it could lose all meaning in the chaos. What makes this more than just a grim thought experiment is the eerie consistency with some observations. Measurements of distant supernova and the cosmic microwave background show dark energy's influence has grown over billions of years. While current data doesn't confirm phantom energy's extreme predictions, it doesn't entirely rule them out either. Some models suggest we're on a knife's edge. If dark energy's equation of state dips just slightly below a critical value, the Big Rip becomes inevitable. Critics argue the theory relies on speculative physics like negative kinetic energy, which has no known natural analogues. Yet phantom energy's terrifying beauty lies in its simplicity. No new dimensions or undiscovered particles needed, just a dark energy field that refuses to play by the rules. Whether it's a real threat or a mathematical curiosity, the Big Rip forces us to confront an unsettling truth: the universe's end might not be a slow fade, but a violent, decisive finale. What if dark energy is nothing more than a cosmic mirage, a trick our equations play on us? That's the radical proposition behind modified Newtonian dynamics, or MN. Instead of inventing an invisible force to explain why galaxies behave the way they do, this theory suggests we've been misunderstanding gravity all along. Think of it like realizing you've been using the wrong map for years. Dark energy might just be a signpost pointing to flaws in our foundational physics. At the heart of MND is a simple but controversial idea. Gravity doesn't weaken as quickly over vast distances as Newton and later Einstein assumed. In the outskirts of galaxies, where stars orbit at speeds that should fling them into the void, something strange happens. Newton's laws predict these stars should slow down, yet they don't. Instead of invoking dark matter to explain this, MN proposes a subtle tweak. Below a certain ultra-weak acceleration threshold, gravity's grip changes, becoming slightly stronger than expected. It's like discovering your car's brakes work differently at slow speeds. Unexpected, but suddenly a lot of erratic driving makes sense. The implications are staggering. If MND is correct, the need for dark energy or even dark matter evaporates. Galactic rotations, cluster motions, even the universe's expansion could all stem from gravity's hidden quirks rather than unseen substances. Supporters point to eerie successes. MN predicted the motions of over 150 galaxies with startling accuracy. No dark matter required. Even Einstein's relativity gets a nod. Some MN variants blend seamlessly with it, suggesting gravity's rulebook might just have unread chapters. But here's the catch: for all its elegance, MN stumbles on cosmic scales. While it nails galaxy behavior, it struggles with the bullet cluster, a cosmic collision where visible matter and gravitational effects clearly separate, as if dark matter were real. And then there's the universe's accelerating expansion, which even modified gravity struggles to explain without some form of dark energy. Critics argue it's like fixing a leaky pipe only to flood the basement, solving one mystery while creating others. Yet MUND refuses to fade away. Newer versions like relativistic MUND or theories invoking emergent gravity keep pushing the boundaries. Maybe gravity isn't a fundamental force at all, but an emergent property of spacetime's deeper structure, like waves rising from an unseen ocean. Whether it's the final answer or just a stepping stone, MUND forces us to ask a humbling question. Are we chasing phantoms because we're too attached to the laws we think we know? What if the missing energy isn't missing at all, just hiding in plain sight in dimensions we can't perceive? This is the mind-bending premise behind higher dimensional theories, where our familiar three-dimensional space is just a tiny slice of a far grander cosmic reality. String theory, the framework that suggests particles are actually tiny vibrating strings, requires at least 10 dimensions to make the math work. So where are these extra dimensions? One possibility is they're curled up so tightly, like the folded layers of an origami masterpiece, that we'd need particle colliders a billion times more powerful to detect them. But another, even wilder idea is that these dimensions aren't small, they're vast, and we're simply trapped on a three-dimensional brane, short for membrane, floating within them. Brane cosmology takes this even further, proposing that our entire universe might exist on one of these membranes drifting through a higher dimensional space called the bulk. Picture it like a slice of bread in an impossible cosmic loaf, with other branes, perhaps entire parallel universes, floating just millimeters away in a dimension we can't access. Here's where dark energy enters the picture. Gravity, unlike other forces, might not be confined to our brane. It could be leaking into these extra dimensions, which would explain why it feels so weak compared to electromagnetism or nuclear forces. If gravity's strength is diluted across unseen dimensions, that could account for the apparent shortage of energy holding galaxies together, no dark matter required. But the real kicker, collisions between branes. Some theorists suggest the Big Bang itself was the result of our brane smashing into another, releasing unimaginable energy that birthed our universe. If true, dark energy might be the lingering ripple of that collision, a cosmic echo still pushing space apart. Others propose that what we perceive as accelerating expansion is actually our brane slowly warping within the bulk, like a sheet of paper curling at the edges. Critics argue these ideas are untestable for now. Without evidence of extra dimensions or brane interactions, they remain thrilling speculation. Yet experiments like the Large Hadron Collider keep searching for signs, like microscopic black holes that would wink into existence if extra dimensions are real. Whether these theories hold up or not, they force us to rethink reality in the most profound way possible. After all, if 95% of the universe is invisible, maybe it's not hiding, we just haven't learned how to see. What if the three-dimensional world we experience is nothing more than an illusion, a cosmic hologram projected from distant two-dimensional boundaries? This is the heart of the holographic principle, a theory so radical it redefines reality itself. Born from the study of black holes, where physicists discovered that all information falling into them gets encoded on their event horizons like data on a celestial hard drive, the principle suggests our entire universe might work the same way. Every star, every galaxy, even your own thoughts could be pixels in a grand cosmic projection, with the true source code existing on a faraway, flat surface we'll never see. Here's where dark energy enters the picture. If the universe really is a hologram, then the accelerating expansion we observe might not be driven by some mysterious force. It could be the result of information density hitting its limits at the boundaries. Think of it like a computer overheating from too much data. As the universe expands, the amount of information needed to maintain the holographic projection grows, stretching the system's capacity. Dark energy, in this view, might be the cosmic equivalent of a lagging video game, the universe's way of struggling to render more detail than its underlying code can handle. The math behind this is staggering. calculations suggest that the maximum information any region of space can hold is proportional not to its volume but to its surface area. That means a sphere the size of a grapefruit contains no more bits than can be etched onto its skin, an idea that flips everyday intuition on its head. If correct, this could explain why dark energy's effect seems so uniform across space. It's not a field or a particle, but a fundamental constraint on how much reality can be encoded at the edges. Critics argue the holographic principle remains untested, more philosophy than physics for now. But experiments like the holometer at Fermilab have tried to detect the pixelation of spacetime itself, hunting for faint jitters in reality that would betray its holographic nature. While no smoking gun has been found, the mere possibility reshapes how we view dark energy. Maybe it's not a thing at all, but a side effect of the universe running out of memory. What makes this theory so compelling is its audacious simplicity. No hidden dimensions, no phantom fields, just the idea that the universe is playing a trick on us, and dark energy is the telltale glitch in the matrix. Whether it holds up or not, the holographic principle forces us to confront a humbling thought. The deepest mysteries of the cosmos might not lie in what we see, but in the invisible boundaries where reality is written. What if the speed of light isn't as constant as we've been taught? That's the daring question at the heart of time-varying speed of light theories, a radical reimagining of one of physics' most sacred rules. Einstein's relativity hinges on light's unwavering speed, but some researchers suggest that in the universe's infancy, light might have raced across space far faster than it does today. This isn't just a tweak to the textbooks, it could rewrite our entire understanding of cosmic expansion, offering an alternative explanation for dark energy's elusive effects. Picture the early universe like a stretched rubber band snapping back into place. If light traveled faster back then, the extra spring in its step could have imprinted effects we now misinterpret as dark energy's push. Proponents argue this solves several puzzles at once: the universe's startling flatness, the evenness of the cosmic microwave background, even the accelerating expansion we observe today, all without invoking mysterious, unseen energy. Instead of dark energy stretching space, maybe we're seeing echoes of light's former sprint, a cosmic hangover from when the rules were different. But here's where physicists hit a wall. The speed of light isn't just some arbitrary number. It's woven into the fabric of reality, tied intimately to electromagnetism, gravity, even causality itself. Alter it, and you risk unraveling everything from nuclear fusion in stars to the stability of atoms. Critics point to stringent constraints. Measurements of distant quasars and gamma-ray bursts show no detectable change in light speed over billions of years. Even subtle variations would have left glaring fingerprints in the cosmic microwave background, distortions we simply don't see, yet the theory refuses to fade. Some versions propose light speed shifted only in the universe's first fractions of a second during the inflationary epoch, leaving today's physics untouched. Others suggest space itself had different properties early on, temporarily permitting faster light without breaking modern relativity. It's a high-stakes gamble if proven. It could demote dark energy from a fundamental force to a cosmic mirage. What makes this idea so tantalizing is its audacity. Science advances when someone dares to question the unshakable, and the speed of light has been untouchable for over a century. Whether it holds up or not, these theories remind us that even the firmest pillars of physics might just be placeholders waiting for the next revolution. Gravity might not be a fundamental force at all. It could be a side effect of chaos, a cosmic illusion born from the universe's relentless slide into disorder. That's the jaw-dropping premise behind entropic gravity, a theory that reimagines one of nature's most familiar forces as a thermodynamic mirage. Picture a crowded room where everyone's jostling for space. The overall movement isn't directed by any single rule, but the collective chaos creates patterns we mistake for order. Now replace the people with atoms and the room with the fabric of space-time, and you've got the essence of this idea. At the heart of entropic gravity lies a concept called the holographic principle, which suggests that information about a volume of space can be encoded on its boundary, like a three-dimensional movie projected from a two-dimensional screen. Dutch physicist Erik Verlaine took this further, proposing that gravity emerges from microscopic changes in this information when objects move. Think of it like a cosmic game of telephone. When a planet or star shifts position, it disturbs the bits of information on the universe's edge, and what we perceive as gravity is just the system rebalancing itself. This isn't just philosophical hand-waving. Verlaine's math reproduces Newton's law of gravitation and even tweaks Einstein's general relativity in subtle ways, all without invoking gravity as a fundamental force. More astonishingly, it might explain dark energy and dark matter without needing invisible substances. If gravity is an emergent property of entropy, then the accelerating expansion of the universe could stem from spacetime's natural tendency to maximize disorder, like gas filling a vacuum. Galaxies' unexplained rotations, just the information on the cosmic horizon adjusting to their presence. But there's a hitch. For all its elegance, entropic gravity struggles with precise predictions. While it broadly matches galaxy rotation curves, it falters at smaller scales, like the motion of stars within dwarf galaxies or the intricate dance of colliding galaxy clusters. Critics argue it's like having a master key that opens most doors but jams at a few crucial ones. And then there's the elephant in the room. If gravity isn't fundamental, why do gravitational waves, ripples in spacetime, behave exactly as Einstein predicted? Supporters counter that science has seen this before. Newton's gravity was once good enough until Mercury's orbit exposed its flaws, paving the way for Einstein. Maybe entropic gravity is the next step in that evolution, a framework waiting for its Mercury moment. Experiments like the Laser Interferometer Gravitational Wave Observatory could hold the answer, hunting for subtle deviations in gravitational waves that hint at an entropic origin. What makes this theory so electrifying isn't just its potential to solve dark energy, it's the audacity to rewrite gravity's origin story. After centuries of treating it as a fundamental force, we're forced to wonder, what if gravity is just the universe keeping score, a ledger of cosmic chaos written in the language of falling apples and orbiting planets? Here's a cosmic 2-for-1 deal. What if dark matter and dark energy aren't separate entities at all, but different faces of the same exotic substance? That's the bold proposition behind Chaplygin gas, a hypothetical perfect fluid that could rewrite the rules of cosmology. Named after Russian scientist Sergei Chaplygin, who studied unusual aerodynamics in the early 20th century, this bizarre substance behaves unlike anything in our everyday experience. At low densities, it clumps together like cold, invisible matter, pulling galaxies into shape. But as the universe expands and matter thins out, it transforms, morphing into a repulsive force eerily similar to dark energy, pushing cosmic structures apart. The magic lies in its equation of state. Ordinary fluids like water or air resist compression, squeeze them, and they push back harder. Chaplygin gas flips this intuition on its head. When compressed, its pressure doesn't rise, it drops. Imagine a sponge that gets softer the more you press it, or a car suspension that absorbs bigger bumps with less resistance. This counterintuitive property lets the gas mimic both dark matter's gravitational grip and dark energy's cosmic push, depending on the circumstances. Early proponents hailed it as the ultimate cosmic unifier, a single elegant solution to two of physics' biggest puzzles. But there's a catch. As observational data piled up, Chaplygin gas began losing its luster. While it handily explains the universe's large-scale structure, it struggles with finer details. Galaxies rotate in ways that pure Chaplain models can't quite replicate, and the cosmic microwave background's intricate patterns don't align neatly with its predictions. Worse still, the gas's transition from matter-like to energy-like behavior happens too abruptly in many models, creating a smoothness problem where the universe ends up looking more homogeneous than what telescopes reveal. Critics argue it's a classic case of too good to be true, a beautiful idea that buckles under real-world scrutiny, yet Chaplain gas hasn't vanished entirely. Some modified versions, like the generalized Chaplain gas, tweak its properties to better fit observations, while others blend it with quantum effects or extra dimensions. It remains a cautionary tale in cosmology. Sometimes the most elegant solutions aren't the right ones, but the pursuit leads us closer to truths we might never have imagined. Water doesn't just boil, it transforms. At a precise temperature, its molecules suddenly reorganize, shifting from liquid chaos to gaseous freedom. Now imagine space itself undergoing a similar metamorphosis, not with heat but with time. This is the startling essence of vacuum metamorphosis, a theory suggesting the universe's expansion might be driven by a cosmic phase transition like the vacuum of space freezing into a new, repulsive state. The idea hinges on quantum gravity, the holy grail of physics that seeks to unite Einstein's relativity with quantum mechanics. In this framework, the vacuum isn't empty, it's a seething quantum foam where spacetime itself fluctuates. Just as water molecules rearrange when ice forms, these quantum fluctuations might have reached a critical threshold in the universe's history, triggering a sudden shift in spacetime's properties. Think of it like walking on a frozen lake that cracks beneath your feet, except the ice is reality itself, and the cracks are dark energy's repulsive force pushing galaxies apart. What makes this theory so compelling is its observational fit. Around 5 billion years ago, the universe's expansion inexplicably accelerated a cosmic speed-up that aligns eerily with vacuum metamorphosis predictions. Proponents argue this wasn't coincidence but a phase transition moment. The math even suggests a telltale signature, a slight deviation from the cosmological constant's perfect uniformity, which upcoming telescopes like the Vera Rubin Observatory could detect. But the real intrigue lies in the quantum gravity connection. Most dark energy theories treat spacetime as static, but vacuum metamorphosis suggests it evolves like a living material. If confirmed, it could offer clues to quantum gravity's nature, bridging the chasm between the infinitely large and infinitesimally small. Critics counter that the theory leans heavily on speculative physics, but its proponents fire back. Sometimes the boldest ideas are the ones that crack reality's deepest puzzles wide open. Imagine the universe not as a smooth, evenly spread canvas, but as a lumpy cosmic sponge, vast voids stretching billions of light years alongside dense galactic filaments. This unevenness isn't just cosmetic, it might hold the key to one of cosmology's biggest illusions. The backreaction hypothesis dares to ask, what if dark energy doesn't exist at all, and we've simply been fooled by the universe's messy architecture? Here's the radical thought at its core. When we measure cosmic expansion, we assume space stretches uniformly like dots on an inflating balloon. But in reality, matter clumps in ways that warp spacetime itself. Gravity's pull slows time in dense regions galaxies, clusters while empty voids expand faster, like gaps in a stretching rubber sheet. When we average these chaotic local effects into a single, smooth universe, the math spits out an apparent acceleration, a phantom signal we've misinterpreted as dark energy's push. It's like judging Earth's terrain by its sea level while ignoring mountains and trenches. The numbers get wilder. Simulations show voids dominate cosmic volume up to 80% of space, while matter crams into the remaining 20%. This imbalance isn't static. As voids grow, their combined negative gravity could mimic dark energy's repulsive force. Picture blowing bubbles in chocolate syrup. the more the bubbles expand, the more the surrounding syrup thins and stretches. If we're inside one of these cosmic bubbles, our measurements might reflect local emptiness rather than universal truth. Critics pounce on a glaring hole. Precision measurements of the cosmic microwave background, the afterglow of the Big Bang, show a universe too uniform for backreaction alone to explain dark energy's observed strength. Yet proponents counter that we're still mapping the universe's true structure, especially massive supervoids like the KBC void, a billion light-year emptiness that might skew our cosmic averages. Others argue general relativity itself needs tweaking when applied to such vast scales, suggesting Einstein's equations might miss subtle backreaction effects when smoothed across billions of light years. This debate isn't just academic, it forces us to confront how we model reality. Cosmology relies heavily on the cosmological principle, the assumption that the universe looks roughly the same everywhere. But if inhomogeneities, those voids and filaments, distort our measurements, dark energy could vanish like a mirage once we account for them. Upcoming galaxy surveys like ESA's Euclid mission might settle the score, mapping the cosmos in unprecedented 3D detail. Until then, the backreaction hypothesis stands as a thrilling reminder. Sometimes the answers aren't in what we see, but in how we choose to see them. Emergent gravity turns our understanding of the universe inside out. What if gravity isn't a fundamental force, but something that arises from the chaos of microscopic interactions, like waves emerging from the churn of ocean currents? At its core, this idea suggests that spacetime itself might be a kind of illusion, a macroscopic pattern woven from countless tiny threads we can't yet see. Think of it like a movie screen. What looks like smooth motion is really millions of pixels flashing in perfect coordination. In this view, dark energy isn't a mysterious substance. It's the side effect of spacetime's hidden machinery creaking under the strain of cosmic expansion. This theory takes entropic gravity's premise that gravity stems from information and disorder, and pushes it further. Instead of attributing gravity to entropy alone, emergent gravity proposes that all of spacetime's properties, from curvature to expansion, bubble up from more fundamental quantum processes. Dutch physicist Erik Verland, who also pioneered entropic gravity, suggests that dark matter's effects, those unexplained galactic rotations, might just be the universe's way of accounting for extra microscopic degrees of freedom we're oblivious to. Imagine a ballet dancer spinning effortlessly. From afar, it looks like magic, but up close, you'd see the muscles, bones, and physics making it possible. Emergent gravity argues we've been watching the cosmic ballet without understanding the dancers. Where this diverges from entropic gravity is scale. Entropic gravity frames gravity as a thermodynamic phenomenon, like heat radiating from a crowded room. Emergent gravity digs deeper, suggesting spacetime itself is built from quantum entanglement, a vast, invisible network of connections between particles. Dark energy, then, could be the tension in that network as the universe stretches, like a spiderweb straining as its threads pull apart. Some models even suggest that this framework could explain why the universe's expansion is accelerating. As spacetime grows, the underlying quantum links thin out, creating a kind of negative pressure that pushes galaxies apart. Critics highlight a glaring challenge. If gravity emerges from quantum information, where's the experimental proof? Unlike entropic gravity, which borrows from well-tested thermodynamics, emergent gravity leans heavily on speculative quantum gravity models. Yet supporters point to tantalizing hints, like the way black holes' properties align with information theory, or how certain quantum materials exhibit emergent phenomena eerily reminiscent of spacetime. The AD-S/CFT correspondence, a theoretical bridge between quantum physics and gravity, even suggests our 3D universe could be a holographic projection of a 2D quantum system, lending indirect support to the idea that gravity isn't fundamental. What makes emergent gravity so electrifying isn't just its potential to explain dark energy, it's the audacity to rewrite physics rulebook from the ground up. If correct, we wouldn't just be adding a new chapter to cosmology, we'd be tearing out the old one and starting fresh. And if wrong, it's still a blazing trail toward the next breakthrough, forcing us to ask, if gravity isn't what we thought, what else might we have misunderstood? Negative mass matter sounds like something straight out of a sci-fi nightmare, particles that don't just resist gravity, but actively push away from everything we know. Picture dropping a ball and watching it shoot upward instead of falling, or a car that accelerates backward when you press the gas. This isn't just weird physics, it's a complete inversion of reality as we understand it. Yet for decades, a handful of theorists have argued that negative mass could be the key to dark energy, a cosmic repulsive force woven into the fabric of the universe itself. The math behind negative mass is both elegant and unsettling. In Einstein's equations, mass curves space-time, creating what we experience as gravity. But if mass could be negative, space-time would curve in the opposite direction, generating a kind of anti-gravity that repels ordinary matter. Unlike dark energy, which permeates space uniformly, negative mass would clump and move like a strange shadow version of normal particles. Galaxies might be surrounded by halos of this phantom substance, pushing them apart like invisible hands. Even more bizarrely, negative mass particles would accelerate in the opposite direction of any force applied to them. Kick one, and it would rocket toward you instead of away. So why hasn't this radical idea taken center stage? For one thing, negative mass wreaks havoc with causality. If such particles existed, they could enable impossible scenarios like perpetual motion machines or time travel-like effects, violating fundamental laws of physics. Laboratory searches have also come up empty. Every known particle, from quarks to neutrinos, adheres to positive mass. Even quantum fluctuations, which can produce temporary, virtual particles, never exhibit negative mass properties. Critics argue that if negative mass were real, its effects would be glaringly obvious. Planets might orbit backward, black holes could spit matter outward, and the universe's structure would look utterly different. Yet the theory persists on the fringes, buoyed by a tantalizing loophole. General relativity doesn't explicitly forbid negative mass. Some models even suggest it could explain dark energy without invoking new fields or dimensions, just a peculiar form of matter hiding in plain sight. Others propose that negative mass particles might be locked away in a parallel sector of reality, interacting with ours only through gravity. It's a long shot, but as the hunt for dark energy stretches on, even the wildest ideas deserve a moment in the spotlight. After all, if 95% of the universe is missing, maybe we need to start considering possibilities that defy common sense. Unparticles sound like something straight out of a cosmic rebellion, particles that refuse to play by the standard rules of mass and dimension. This bizarre concept comes from the mind of physicist Howard Georgi, who proposed that certain hidden sectors of reality might operate under radically different laws, with forces that don't conform to whole number dimensions. Think of it like this: if ordinary particles are musicians in a symphony, unparticles are the avant-garde soloists, bending and breaking the composition in ways we can't predict. And here's where dark energy enters the stage, because if these fractional dimensional entities exist, their peculiar influence might be driving the universe's runaway expansion. The math behind unparticles is as beautiful as it is strange. In our familiar three-dimensional world, forces like gravity and electromagnetism weaken with distance in predictable ways. Gravity follows an inverse square law, for example. But unparticles could obey fractional power laws, meaning their influence might fade at a rate like 1 over distance to the power of 1.6 or some other non-integer value. This tiny tweak to the exponent creates cascading effects, especially over cosmic scales. Imagine stirring honey with a spoon. The resistance you feel depends on how the liquid's viscosity interacts with the spoon's motion. Now replace honey with space-time and the spoon with unparticles, and you've got a crude analogy for how these entities could subtly thicken the cosmos, altering how energy propagates and potentially mimicking dark energy's repulsive push. What makes this theory so intriguing is its flexibility. Unlike the cosmological constant, which rigidly stays the same everywhere, unparticles could clump or spread in response to the universe's expansion, creating dynamic effects. Some models suggest they might interact weakly with known particles, producing faint signatures in high-energy particle collisions. Others propose that unparticles could arise from hidden dimensions. Those curled-up layers of reality string theory suggests might exist, leaking their fractional behavior into our observable universe. It's as if the cosmos has a secret backstage where the laws are written in a language we're only starting to decipher. Yet for all its elegance, unparticle physics faces a steep uphill battle. No experiment has ever detected fractional dimensional behavior, and the theory leans heavily on speculative extensions to the standard model. Critics argue it's a solution in search of a problem, an elaborate mathematical framework without observational hooks. But supporters counter that the same was once said about neutrinos or gravitational waves, both of which were theorized long before detection. The Large Hadron Collider and future experiments like the proposed Future Circular Collider could change the game, hunting for anomalies in particle jets or missing energy events that might hint at unparticles' shadowy presence. Whether unparticles are real or just a fascinating mirage, they force us to confront a humbling truth. The universe might be stranger than we've dared to imagine. If even a fraction of our dimensions can bend the rules, what other hidden layers are waiting to rewrite the cosmic script? What if dark matter and dark energy aren't separate enigmas at all, but two faces of the same shadowy entity? That's the provocative idea behind dark fluid, a theory proposing that the universe's missing 95% is neither particle nor field, but an exotic, unified substance with a split personality. Picture it like cosmic quicksilver. In regions where matter clusters, this fluid acts like a gravitational glue, mimicking dark matter's pull. But in the vast, empty voids between galaxies, it flips its nature, becoming repulsive and accelerating expansion, just like dark energy. One substance, two radically different behaviors, all depending on where it finds itself in the cosmos. This idea isn't entirely new. Chaplain gas, that cosmic chameleon we discussed earlier, hinted at the possibility of a unified dark sector. But dark fluid takes it further, treating the mysterious components not as distinct phenomena with separate equations, but as different phases of a single underlying reality. Imagine water, steam in a kettle, ice in a freezer, liquid in a glass, all H2O, just manifesting differently under varying conditions. Dark fluid theorists argue the universe's missing energy might work the same way, shifting its role based on the density of its surroundings. The math behind this is both elegant and fiendishly complex. Dark fluid models often rely on relativistic elasticity, treating space-time as a kind of stretchy fabric that resists deformation in dense areas, creating gravity-like effects, but pushes back in empty ones, driving acceleration. Some versions even tie it to quantum vacuum effects, suggesting the fluid's properties emerge from microscopic fluctuations in the fabric of reality itself. It's a bold synthesis, weaving together gravity, quantum mechanics, and cosmology in ways that could, if proven, unify physics' biggest disjointed theories. But here's where the theory hits turbulence. Observational data throws up stubborn roadblocks. While dark fluid neatly explains large-scale cosmic acceleration, it struggles with the finer details of galaxy rotation curves, the very observations that first cemented dark matter's existence. Stars orbit galactic centers too fast for their visible mass, and pure dark fluid models can't always replicate those speeds without tweaking. Worse, the cosmic microwave background's precise temperature patterns, which align beautifully with standard dark matter models, become jagged and inconsistent under some dark fluid frameworks. Critics argue this makes dark fluid a jack of all trades but master of none, too flexible to falsify, yet not precise enough to triumph over existing theories. Supporters counter that we're still learning how to test it. Upcoming galaxy surveys might reveal subtle fingerprints, like peculiar correlations between void expansion rates and galactic motions that could tip the scales. Others suggest dark fluid might need a quantum twist, perhaps interactions with hypothetical particles we've yet to discover. What makes dark fluid so tantalizing isn't just its potential to simplify cosmology's messiest problems. It's the philosophical shift it demands, that the universe's greatest mysteries might not be separate puzzles, but pieces of a single, deeper truth we've yet to grasp. Whether it's the final answer or just a stepping stone, dark fluid challenges us to think bigger, to imagine that darkness in all its forms might be more connected than we ever dreamed. Deep in the fabric of space, where matter thins to near nothingness, an invisible switch might be flipping, triggering a hidden force that pushes the cosmos apart. Enter symmetrons, hypothetical particles so light they barely register as matter, yet potentially powerful enough to explain dark energy's mysterious push. These aren't your average particles, they're cosmic chameleons, changing their behavior based on the density of their surroundings. In crowded galactic neighborhoods, symmetrons stay quiet, hiding their effects. But in the vast, empty voids between galaxies, they awaken, unleashing a repulsive force that could be driving the universe's accelerating expansion. The symmetron's magic lies in its connection to symmetry breaking, a phenomenon that shapes everything from magnets losing their pull when heated to the way particles gained mass after the Big Bang. Picture a marble resting atop a perfectly smooth hill. In dense regions of the universe where matter's gravity dominates, the symmetron's hill stays balanced and the particle exerts almost no influence. But as space expands and matter dilutes, that hill suddenly develops valleys. The marble rolls down, and the symmetron's energy switches on, creating a gentle push against gravity. It's like a cosmic pressure valve, one that only activates when the universe grows sparse enough to need it. What makes this theory so compelling is how neatly it sidesteps dark energy's thorniest problems. Unlike the cosmological constant, which stubbornly insists empty space has fixed energy, symmetrons adapt. They explain why dark energy's effects only became noticeable a few billion years ago, because that's when the universe's expansion crossed a threshold, making voids large enough for symmetrons to flip their switch. Even more intriguing, these particles could leave fingerprints in precision laboratory experiments. Since symmetrons interact weakly with ordinary matter, they might subtly alter the forces between atoms in ultra-sensitive vacuum chambers, a whisper of their presence that experiments like the Casimir effect or atom interferometry could one day detect. Yet skeptics highlight glaring challenges. If symmetrons are so light, why haven't particle colliders spotted their telltale signatures? And how do they avoid clashing with the exquisite precision of the cosmic microwave background, which so far shows no evidence of their proposed density-dependent effects? Supporters counter that symmetrons might couple to matter far more weakly than even neutrinos, making them ghosts in the machine, present but nearly impossible to spot without revolutionary new detectors. Others speculate they could be tied to extra dimensions, their full effects only manifesting across scales larger than our current telescopes can probe. The symmetron hypothesis forces us to confront a humbling possibility, that the universe's expansion isn't driven by some monolithic, unchanging force, but by a dynamic entity that watches and reacts, a cosmic thermostat adjusting its output as space itself evolves. Whether real or just a beautiful mathematical mirage, symmetrons remind us that the answers to cosmology's biggest mysteries might not lie in brute strength, but in subtlety, particles so light they barely exist, yet whose influence shapes the fate of everything. Actions and chameleon fields sound like creatures from a fantasy novel, but they might hold the key to one of physics' greatest puzzles. These aren't your everyday particles, they're shape shifters, adjusting their properties based on their surroundings in ways that could explain dark energy's elusive behavior. Take actions first proposed to solve a problem in quantum physics entirely unrelated to cosmology. These ultra-light particles were imagined to preserve a delicate symmetry in the subatomic world, but researchers soon realized they could do far more. In the dense heart of a galaxy, actions would behave like featherweight dark matter, subtly bending starlight and influencing orbits. But in the vast emptiness between galaxies, their collective energy might stretch spacetime itself, mimicking dark energy's expansive push. The real magic happens when actions roll down their potential energy landscape, a concept that might sound abstract but behaves like a cosmic game of downhill. Picture a ball resting on a sloping surface covered in tiny bumps. In crowded regions, the ball gets stuck in a small dip, barely moving. This is the action acting like a lightweight particle. But as the universe expands and matter thins out, the ball breaks free, rolling smoothly down the slope, converting its stored energy into a force that nudges space apart. This slow roll could perfectly match the gentle acceleration we observe, explaining why dark energy's effects only became noticeable billions of years after the Big Bang. Chameleon fields take this adaptability to another level. Named for their ability to hide in dense environments, these fields change their mass based on the local matter density, like a spy blending into different crowds. Near Earth or within galaxies where matter is tightly packed, chameleons would be massive and nearly undetectable, their effects dwarfed by gravity. But in the void between galactic clusters, their mass could drop to nearly zero, unleashing a repulsive force strong enough to accelerate cosmic expansion. It's as if space itself has moods, shifting between attraction and repulsion depending on its emptiness. Critics point out a major hurdle. If these fields are so sensitive to their environment, why haven't we spotted their effects in laboratory experiments? Action searchers using ultra-sensitive magnetic chambers and chameleon probes with atom interferometers have come up frustratingly empty. Some theorists argue we might be looking for the wrong signatures. Perhaps these particles interact even more weakly than we've assumed, or maybe their effects are masked by other cosmic noise. Others suggest our experiments simply aren't large or precise enough yet to catch such subtle shifts. Yet the allure of these theories lies in their elegance. Unlike static solutions like the cosmological constant, actions and chameleons offer dynamic explanations that evolve with the universe. They paint a picture where dark energy isn't a fixed feature of space, but a dance between particles and their environment, a dance we're only beginning to hear the music for. Whether these ideas hold up or not, they remind us that the universe's secrets might not lie in brute force, but in whispers too quiet for our current tools to hear. The cosmological constant is having an identity crisis. What if Einstein's so-called biggest blunder isn't just real but unstable? That's the provocative idea behind running lambda, a theory suggesting dark energy might be slowly leaking away, its strength diminishing as the universe ages. Imagine a battery powering cosmic expansion, except it's not holding its charge. Every billion years, the push driving galaxies apart weakens just a fraction, like a fading echo of the Big Bang's initial roar. This isn't just idle speculation. Quantum field theory hints that the vacuum energy underlying the cosmological constant shouldn't stay frozen. It ought to fluctuate, decay, or interact with other fields over time. Think of it like a mountain eroding under rain. Even the most rigid structures change when exposed to enough time and energy. If lambda runs, its decline could explain why dark energy's dominance is a relatively recent cosmic development, only overtaking gravity's grip a few billion years ago. The smoking gun would be subtle shifts in how fast the universe expands at different epochs. Astronomers hunt for these clues by comparing supernova in distant galaxies, the cosmic microwave background's faint wrinkles, and the large-scale distribution of matter. A decaying lambda would leave fingerprints in this data, perhaps a slight mismatch between how quickly voids grow versus how tightly galaxies cluster. Some tantalizing but still debated observations even suggest dark energy's strength might have dropped by around 10% over the last 2 billion years, though the evidence remains far from conclusive. Critics argue that a running lambda introduces more problems than it solves. If vacuum energy decays, where does that energy go? Does it vanish entirely, violating conservation laws, or transform into something else? Others point out that most quantum corrections predict lambda should change absurdly fast, trillions of times quicker than observations allow. But supporters counter that unknown symmetries or higher dimensional effects might act as cosmic regulators, slowing the decay to a barely perceptible trickle. What makes running lambda so compelling is its audacious blend of humility and ambition. It admits our simplest model, a perfectly constant dark energy, might be incomplete while offering a bridge to deeper physics. Whether proven or not, this theory forces us to confront a radical thought. The universe's expansion might not be propelled by some immutable force, but by an energy that's quietly, imperceptibly fading into the cosmic background. Black holes are cosmic paradoxes, collapsed stars so dense even light can't escape their grip, yet they might secretly be the engines driving the universe's expansion. This mind-bending idea flips everything we thought we knew about these gravitational monsters on its head. Forget dark energy as some mysterious field permeating empty space. What if the answer's been lurking in the darkest corners of the cosmos all along, inside black holes themselves? The theory hinges on a startling revelation. Black holes might contain vacuum energy in their cores, not the kind of energy that powers stars, but something far stranger, a relic from the early universe trapped when these behemoths formed. Picture a black hole not just as a pit of annihilation, but as a cosmic battery, storing energy so potent it warps spacetime itself. Recent studies analyzing supermassive black holes at galactic centers found something eerie. Their growth over cosmic time aligns suspiciously well with the universe's accelerating expansion. It's as if every time a black hole swallows matter, it's not just getting heavier, it's somehow contributing to dark energy's push. Here's how it could work. Einstein's equations allow for black holes to have an internal cosmological constant, a kind of pressurized energy that resists gravity's crush. Normally, this energy stays locked away behind the event horizon. But as the universe expands and black holes merge or consume matter, their combined internal energy might leak into the cosmos, not as radiation or jets, but as a subtle repulsive force stretching spacetime. Think of it like squeezing a balloon. The pressure inside doesn't vanish, it just redistributes. The implications are staggering. If true, dark energy isn't some abstract background field, it's the collective breath of every black hole exhaling spacetime outward. This could explain why cosmic acceleration kicked off when it did, around 5 billion years ago. By then, the universe had cooled enough for supermassive black holes to dominate, their combined energy reaching a tipping point where their push overtook gravity's pull. Even the infamous Hubble tension, the mismatch in how fast different methods measure the universe's expansion, might find an answer here as black hole distributions vary across cosmic time and space. Critics pounce on a glaring question: how could anything escape a black hole's grasp to influence the wider universe? Proponents argue it's not about particles breaking free, but the black hole's gravitational field itself changing. As vacuum energy builds inside, it might subtly alter how the black hole curves spacetime around it, like a heavy object resting on a trampoline that starts to stiffen the fabric beneath. Others counter that black holes are too sparse to account for dark energy's smooth, uniform effects unless there's a hidden population of primordial black holes we've yet to detect. The real test lies in upcoming gravitational wave observatories. If black holes truly fuel cosmic acceleration, their mergers should leave faint imprints in the ripples of spacetime, hints of extra dimensions or exotic matter in their cores. Already, telescopes like LIGO and Virgo are hunting for anomalies in black hole collisions that might betray this dark energy connection. Whether the theory holds or collapses under scrutiny, it forces us to reconsider black holes not as endpoints, but as active players in the universe's grand evolution. A reminder that sometimes the darkest places hold the brightest secrets. What if the universe has a hidden twin, a perfect mirror version of reality where everything spins the opposite way, time flows backward, and the laws of physics play out in reverse? This isn't just wild speculation, it's a serious idea rooted in the concept of parity symmetry, the principle that the universe should treat left and right as interchangeable. In the 1950s, physicists were shocked to discover this symmetry breaks down in weak nuclear interactions, meaning the cosmos has a subtle preference for one direction over the other. But what if that violation isn't a flaw, it's a clue? Some theorists propose that dark energy might actually be the gravitational echo of a mirror universe bleeding into ours, like sound leaking through a shared wall between apartments. The math behind this is as elegant as it is bizarre. If a mirror universe exists, its particles would interact with ours exclusively through gravity, the only force that could traverse the divide. Every star, every galaxy in our reality would have a counterpart in that shadow realm, identical in mass but flipped in charge, spin, and even the flow of time. Over billions of years, the expansion of their universe could tug on ours through these faint gravitational links, creating the illusion of dark energy's repulsive push. Picture two stretched rubber sheets stacked together. As one expands, it subtly drags the other along, even though they never truly touch. Here's where it gets even stranger. Because this mirror universe would obey opposite quantum rules, its very existence could explain one of physics' most puzzling fine-tuning problems: why the cosmological constant is so unnervingly small. In our world, vacuum energy should be colossal, but if an equal and opposite vacuum energy exists next door, the two might cancel out almost perfectly, leaving behind just the faint residue we call dark energy. It's like two singers hitting identical notes out of phase. Their voices don't add up to a louder sound, they vanish into silence. Yet for all its theoretical charm, mirror universe leakage faces a brutal challenge. It's virtually untestable. Since the only interaction between realities would be gravitational, and any signal would be drowned out by the noise of ordinary matter, we'd need detectors sensitive enough to pick up a whisper in a hurricane. Even the faintest traces, like anomalies in the cosmic microwave background or distortions in gravitational wave patterns, could have mundane explanations. Critics argue it's less a theory and more a metaphysical escape hatch, a way to hand-wave the unknown without offering a clear path to verification. But supporters counter that untestability today doesn't mean impossibility tomorrow. Future quantum gravity experiments or hyper-precise spacecraft tracking might one day spot the telltale tremors of a mirror universe's influence. Until then, this idea lingers at the edge of science, a tantalizing reminder that the universe's greatest mystery might not be missing energy at all, just energy we're borrowing from a stranger in the cosmic dark. Neutrinos are the universe's ultimate ghosts, particles so elusive they pass through entire planets like they're not even there. Billions stream through your body every second, leaving no trace. Yet these cosmic phantoms might hold a shocking secret. Their elusive nature could be the key to dark energy itself. The idea hinges on neutrinos' most baffling trait: they shape-shift as they travel, oscillating between different types in a quantum dance we're only beginning to understand. But what if this metamorphosis isn't just a subatomic quirk? What if, on a cosmic scale, their shifting properties are warping spacetime itself? At the heart of this theory lies one of physics' most puzzling observations. Neutrinos have mass but barely any. Unlike electrons or quarks, which have well-defined weights, neutrinos are feather-light, millions of times lighter than the next lightest particle. Even stranger, their masses seem to change depending on how far they've traveled or how dense their surroundings are. Picture a chameleon that doesn't just change color, but alters its very substance as it moves from jungle to desert. Now imagine trillions of these particles flooding the cosmos, their collective weight subtly shifting as the universe expands. Over billions of years, that tiny fluctuation could add up, creating a pressure that nudges galaxies apart. The math is as elegant as it is unorthodox. In dense regions like galaxy clusters, neutrinos would behave like ordinary particles, contributing weakly to gravity. But in the vast voids between galaxies where matter is sparse and space stretches thin, their quantum weirdness could take over. Some models suggest their masses might effectively drop to near zero in these emptinesses, releasing stored energy that acts like a cosmic repellent. It's as if the universe has built-in shock absorbers, softening gravity's grip where matter thins out. This could explain why cosmic acceleration kicked off when it did, around 5 billion years ago, the moment neutrino densities in voids crossed a critical threshold, like a phase transition in an invisible ocean. Critics raise a glaring objection. Neutrinos are too lightweight to wield such cosmic influence. Even if every neutrino in the universe suddenly doubled its mass, their combined gravitational effect would still be dwarfed by dark energy's observed strength. But supporters counter that we might be underestimating neutrino interactions. If these particles couple to hidden fields or extra dimensions, their true impact could be amplified, like whispers in a cave echoing into thunder. Others propose that sterile neutrinos, hypothetical, heavier cousins of the ones we've detected, could be the real players, their presence warping spacetime in ways ordinary neutrinos can't. The smoking gun might lie in relic neutrinos from the Big Bang. These ancient particles, cooled to near absolute zero, should saturate the cosmos like a faint background glow. If neutrino dark energy is real, their distribution would bear telltale irregularities, clumps and voids that trace the universe's accelerating expansion. Experiments like Ptolemy and future neutrino observatories aim to catch these ghosts in the act, hunting for deviations from theoretical predictions. Even more tantalizing, certain neutrino mass models predict subtle twists in the cosmic microwave backgrounds, polarization patterns, fingerprints that next-gen telescopes like the Simons Observatory could uncover. Whether this theory holds or collapses, it forces us to confront a humbling truth. The answers to cosmology's biggest mysteries might not lie in the colossal or the exotic, but in the barely there, particles so insignificant they were once dismissed as cosmic afterthoughts, yet whose quantum whispers could be shaping the fate of everything. What if gravity doesn't play by the rules we think it does? Forget pulling objects together in a predictable, local way. What if its influence can stretch across the cosmos instantly, like a hidden network connecting everything in the universe? That's the radical premise of non-local gravity, a theory suggesting that what we perceive as dark energy might actually be gravity's long-range whispers, echoing from one corner of spacetime to another without delay. This idea turns Einstein's general relativity on its head. In his framework, gravity travels at the speed of light, warping spacetime like a bowling ball resting on a trampoline, tugging nearby objects inward with a force that diminishes over distance. But non-local gravity proposes something far stranger that the universe remembers. Every gravitational interaction leaves a faint imprint on spacetime, and those imprints can resonate across vast distances, creating effects that mimic dark energy's repulsive push. Picture throwing a pebble into a pond, except the ripples never fade, they linger, stacking up over billions of years until their combined force starts pushing other ripples apart. The math behind this is as beautiful as it is daunting. Equations that once described gravity as a local force now include terms for memory or retardation, accounting for how past events subtly tweak present interactions. Some models even suggest that the universe's acceleration isn't driven by a mysterious energy, but by the cumulative gravitational echoes of long-dead stars and galaxies, their influence preserved in space-time like fossils in amber. It's as if the cosmos is a vast, interconnected machine where every gear's motion, no matter how ancient, still subtly turns the others. But critics pounce on a glaring issue. Non-locality violates causality, the bedrock principle that cause must precede effect. If gravity acts instantly across cosmic distances, it opens the door to paradoxes like a star's death today influencing another's orbit a billion years ago. Relativity's insistence that nothing outpaces light isn't just dogma. It's been tested relentlessly, from GPS satellites to the timing of pulsars. Even quantum entanglement, which famously allows spooky action at a distance, doesn't permit faster than light communication. Non-local gravity would require rewriting physics in ways that make most theorists deeply uneasy. Yet supporters counter that nature has surprised us before. Quantum mechanics shattered classical intuitions a century ago. Maybe gravity is due for its own revolution. They point to tantalizing hints like anomalies in galaxy rotations or odd correlations between distant supernovae that could hint at non-local effects. Others argue that non-locality might only manifest on cosmic scales, invisible in the lab but dominant across the vastness of intergalactic space, a bit like how you'd never notice Earth's curvature in your backyard, but it's undeniable from orbit. Whether this theory holds up or not, it forces us to confront a humbling possibility. That gravity, the force we thought we knew best, might be hiding layers of complexity we've only begun to glimpse. After all, if 95% of the universe is missing, maybe the problem isn't what's out there, it's how we've been looking. Cosmic strings sound like something from an astrophysical thriller, threads of pure energy thinner than an atom yet stretching across the entire observable universe. These hypothetical relics from the Big Bang aren't just sci-fi fodder. They might be lurking in the cosmic background, subtly warping space-time and contributing to the very energy we've labeled dark. Picture the aftermath of freezing. A lake cracks form as the ice contracts, creating jagged lines of tension. Now imagine the universe cooling from its fiery birth, and instead of ice, space-time itself developing cracks, minuscule, infinitely long defects vibrating with the leftover energy of creation. These strings wouldn't behave like ordinary matter. With mass densities of 100 million billion tons per centimeter, a single cosmic string could slice through a planet like a wire through cheese, leaving gravitational wakes detectable as twin images of distant galaxies or abrupt jumps in the cosmic microwave background. But here's the twist: as they vibrate, snap, or loop, cosmic strings could release bursts of gravitational energy, not enough to explain all of dark energy, but enough to contribute to the cosmic budget in ways we've barely begun to map. It's as if the universe has a hidden economy of energy, and these strings are the untaxed transactions. Contrast this with inflation, the leading theory for the universe's exponential expansion in its first moments. Inflation predicts a smooth, uniform cosmos where any primordial defects like strings would be stretched to irrelevance. Yet if cosmic strings exist, they'd challenge that pristine picture, hinting that inflation wasn't perfectly even, or that it ended with phase transitions violent enough to leave scars in spacetime. Some models even suggest strings could be hybrids, formed later when dark energy fields underwent symmetry-breaking phase changes, like cracks forming in drying mud. These dark strings would interact solely through gravity, weaving unseen through galaxies while subtly tweaking their motions. The hunt for cosmic strings is already underway. Telescopes scour the sky for telltale distortions, sudden jumps in starlight, or unexplained ripples in gravitational wave detectors. Even more tantalizing, certain string configurations could produce ultra-high frequency gravitational waves, a signature future observatories like LISA or the Einstein telescope might catch. If found, they wouldn't just rewrite cosmology's origin story. They'd prove that dark energy isn't a singular mystery, but a patchwork of phenomena, some primordial, some dynamic, all woven into the fabric of reality itself. Whether cosmic strings are out there or not, their theoretical allure forces us to confront a deeper truth. The universe's missing energy might not be missing at all. It could be hiding in plain sight, woven into defects so subtle we've only just begun to trace their outlines. What if the weight of the universe isn't constant? That's the startling premise behind variable mass theory, an idea suggesting that the very building blocks of reality might be subtly lightening or heavying with cosmic time. Imagine stepping on a scale each morning, only to find your mass mysteriously shifting by a fraction of a gram. Now extrapolate that to every atom in existence, and you've got a radical explanation for dark energy's grip on the cosmos. This theory traces its roots to physicist Paul Dirac's large number hypothesis, an odd observation from the 1930s that certain cosmic ratios, like the ratio of the electromagnetic force to gravity, hover around incomprehensibly huge numbers like 10 to the power of 40. Dirac proposed these weren't coincidences, but clues that fundamental constants might evolve as the universe ages. Fast forward to today, and some researchers argue mass could be that variable. If particles like electrons or quarks were even slightly heavier in the early universe, gravity's pull would have been stronger, slowing expansion. Then, as masses decayed to their current values, gravity's grip would weaken, allowing dark energy's repulsive push to dominate. It's like a cosmic game of tug-of-war where one team gradually loses strength over billions of years. The mechanics get wilder when you consider how mass originates. In the Standard Model, particles get their heft from interactions with the Higgs field, an invisible energy syrup permeating space. If that field's properties shift over time, perhaps due to quantum effects or interactions with hidden dimensions, particle masses could drift. Picture a bowl of syrup left in the sun. As it thickens or thins, objects passing through it would sink differently. Similarly, a Higgs field in flux might let stars and galaxies weigh less today than they did in the ancient universe, altering how they curve spacetime. Observational clues tantalize but frustrate. Ancient starlight from distant quasars shows atomic spectra matching modern values, suggesting electron masses haven't budged more than a few parts in a million over billions of years, yet even that tiny wiggle room could matter. Other studies hunt for discrepancies in the cosmic microwave background's temperature patterns or anomalies in the orbits of pulsars, which should wobble differently if their masses were variable. Critics argue these effects would have been spotted by now if they existed, but supporters counter that shifts might be subtle or localized, like a cosmic tide ebbing only in the voids between galaxies. The theory's boldest twist: it could unite dark energy and dark matter under one roof. If some particles lose mass while others gain it, say, ordinary matter lightens while hypothetical dark matter particles grow heavier, their competing gravitational influences might mimic both phenomena. It's a cosmic seesaw where the balance of weight dictates the fate of expansion. Whether variable mass holds up or collapses under scrutiny, it forces us to confront a profound question. Are the rules of reality truly eternal, or are they quietly, imperceptibly changing beneath our feet? The universe might be running out of memory, not in a metaphorical sense, but literally hitting a hard limit on how much information it can store. This bizarre idea stems from the holographic principle, which suggests reality's true blueprint isn't three-dimensional but encoded on a two-dimensional boundary, like a cosmic DVD holding the data for our 3D experience. Apply this to dark energy, and you get holographic dark energy, a theory claiming the universe's accelerating expansion isn't driven by a mysterious force, but by space-time straining against its own informational constraints. At the heart of this theory lies a simple but radical equation. Normally, dark energy's density is modeled as constant or evolving with time, but holographic dark energy ties it directly to the universe's event horizon, the maximum distance from which light could ever reach us. The formula suggests dark energy's strength isn't arbitrary. It's proportional to the inverse square of this horizon size. Picture a balloon inflating. As the surface area grows, the rubber stretches thinner. Similarly, as cosmic space expands, the density of information pixels per unit volume drops, creating a kind of cosmic lag that manifests as repulsive energy. What makes this approach so compelling is how it sidesteps dark energy's biggest headache, the cosmological constant problem. Quantum field theory predicts vacuum energy should be orders of magnitude stronger than observed, but holographic dark energy naturally limits itself. The universe can't pack more energy than its informational surface area allows, just like a hard drive can't store more data than its capacity. This cosmic error message might explain why dark energy is so faint. It's not a field or particle, but a system warning that spacetime is approaching its rendering limits. Yet critics highlight glaring holes. For one, the holographic principle itself remains unproven, resting on speculative string theory math. Worse, the model's predictions often clash with observations. It struggles to explain why dark energy's effects only became dominant 5 billion years ago, or why galaxy clusters exhibit specific gravitational lensing patterns that standard dark matter models nail precisely. Some variations tweak the formula by adding extra terms, like accounting for quantum corrections or interactions with dark matter. But these patches risk making the theory untestable, a mathematical Rorschach blot that can be adjusted to fit any data. Supporters counter that we're judging the theory too soon. Upcoming telescopes like the Vera-Rubin Observatory could spot subtle discrepancies in how voids expand versus how galaxies cluster, potential fingerprints of holographic effects. Others suggest the theory might merge with entropic gravity, where dark energy emerges from spacetime's thermodynamic properties rather than pure information limits. It's a long shot, but so was quantum mechanics a century ago. Whether holographic dark energy holds up or not, it forces a profound rethink of cosmic acceleration. Maybe the universe isn't being pushed apart by some exotic substance, but constrained by its own underlying code, a cosmic processor struggling to render an ever-expanding reality. The answer to dark energy might not lie in what's filling space, but in the invisible boundaries defining how much space can even exist. What if our entire universe, every star, every galaxy, even the very concept of dark energy, is nothing more than lines of code in an unfathomably advanced simulation? This is the spine-tingling premise of the simulation hypothesis, a theory that takes the mystery of missing energy and flips it on its head. Forget exotic particles or hidden dimensions. Dark energy might just be a rounding error in someone else's cosmic computer, a subtle glitch in the rendering of our virtual reality. Think of it like this: when a video game strains your graphics card, textures might flicker or objects pop in and out of existence. Now imagine the same thing happening at the scale of the cosmos. The universe's accelerating expansion, that could be the simulation's processors struggling to maintain consistent physics across billions of light years, leaving gaps we interpret as dark energy. Even the notorious cosmological constant problem, where quantum physics predicts vacuum energy should be astronomically stronger than observed, makes eerie sense under this lens. The simulators might have dialed it down intentionally, like adjusting a slider in a universe building software to prevent catastrophic crashes. But how would this even work? Proponents point to unsettling parallels between our universe and virtual worlds. Quantum mechanics already suggests reality is pixelated at the smallest scales, with discrete packets of energy and a fundamental limit to how precisely we can measure anything. The holographic principle that all information in a volume of space might be encoded on its boundary sounds suspiciously like how a 3D game engine renders environments from 2D data. Even dark matter's elusive nature fits the narrative. It could be placeholder code, a temporary fix holding galactic structures together until the next patch. Not surprisingly, the scientific pushback is fierce. Critics argue the simulation hypothesis is unfalsifiable, a slick, modern-day version of God did it that offers no testable predictions. If the simulators can alter reality at will, how could we ever prove we're in a simulation? Others highlight glaring inconsistencies. Why would an advanced civilization waste computing power simulating empty cosmic voids or the tedious evolution of stars? And if dark energy is a glitch, why does it follow such precise, mathematically elegant patterns, like the near-perfect fit of the cosmological constant to supernova data? Philosophers counter with their own barbed questions. If we're in a simulation, who's running it? And why are they themselves simulations in an infinite regression of nested realities? The hypothesis leans heavily on anthropic reasoning. We'd only be aware of a simulation if it were stable enough to produce conscious observers, which might explain why physical constants seem improbably fine-tuned for life. But this skirts uncomfortably close to solipsism, the idea that only one's mind is sure to exist. Yet beneath the skepticism lies a fascinating truth. The simulation hypothesis, for all its sci-fi flair, forces us to confront the limits of human knowledge. Dark energy's persistence might not point to a glitch in the universe, but a glitch in our understanding, a reminder that reality, simulated or not, still holds mysteries we've barely begun to unpack. Whether you find the idea thrilling or absurd, it underscores one certainty: the universe's greatest puzzles refuse to be solved easily. Of all the theories trying to unravel dark energy's mystery, 3 stand out not just for their creativity, but for how stubbornly they match what we actually observe. First up, quintessence, the shape-shifting dark energy that refuses to sit still. Unlike the rigid cosmological constant, quintessence evolves over time, acting more like a cosmic chameleon than a fixed force. Imagine a volume knob for the universe's expansion, sometimes turned high during rapid inflationary periods, other times dialed down to a whisper. This flexibility lets quintessence explain why dark energy's dominance is a relatively recent cosmic development. Observations of ancient supernova fit neatly into its framework, showing acceleration kicking into gear around 5 billion years ago, but there's a catch. For all its adaptability, quintessence struggles with fine-tuning. Why does its energy density today align so perfectly with critical cosmic thresholds? And why haven't we detected the subtle variations in its strength that the theory predicts? It's like having a keyboard where one key plays a symphony, convenient but suspiciously precise. Then there's modified gravity, the rebel of the group, arguing we've been misreading cosmic expansion from the start. Instead of inventing dark energy, this theory suggests Einstein's equations need a tweak on galactic scales. Picture trying to navigate with an outdated map. Modified gravity claims we've been using the wrong coordinates for the cosmos. Its biggest triumph, explaining galaxy rotations without invoking dark matter, thanks to frameworks like MN. But when it comes to the universe's large-scale structure, cracks appear. The bullet cluster, a cosmic collision where gravity's effects separate visibly from normal matter, poses a glaring challenge. Modified gravity can't easily explain this smoking gun observation without awkward contortions. Worse, most versions still need some form of dark energy to account for accelerating expansion, leaving the theory stuck between revolution and compromise. The wildcard contender, the holographic principle, which reimagines dark energy as a cosmic storage issue. If the universe is a projection from a two-dimensional boundary, like a 3D movie encoded on a flat DVD, then accelerating expansion might reflect the system straining against its information limits. It's a radical solution to the cosmological constant problem, capping vacuum energy naturally. But here's the rub. Holographic dark energy predicts subtle deviations in how voids expand versus galaxy clusters, deviations we haven't convincingly spotted yet. Without empirical hooks, it risks floating in the realm of elegant mathematics rather than observable reality. So who's winning? Quintessence leads in flexibility, modified gravity in audacity, and the holographic principle in sheer creativity. But until new data from next-gen telescopes or particle colliders tips the scales, these three remain locked in a cosmic stalemate, each brilliant, each flawed, and each reminding us that the universe's greatest mysteries refuse to surrender easily. Trying to unravel dark energy is like detective work where the clues are hidden in invisible ink and the crime scene spans billions of light years, the first hurdle. Our tools are laughably crude compared to the universe's grandeur. Imagine studying a snowflake with oven mitts. That's roughly the challenge astrophysicists face when probing a force that permeates all of space but leaves no direct fingerprints. Our best instruments, space telescopes like Hubble and JWST, galaxy surveys like DAISY are revolutionary, yet they're still peering through a keyhole at a phenomenon that operates on scales dwarfing human comprehension. Take cosmic timescales. Dark energy's effects play out over eons, while we've been observing the cosmos in detail for barely a century. It's like watching a single frame of a million-year movie and trying to guess the plot. The universe's acceleration didn't even become detectable until 5 billion years ago. Before that, gravity's grip masked its subtle push. To complicate things, dark energy's strength might not be constant. What if it's fading or fluctuating? Confirming that would require measurements so precise they border on impossible with current tech, like weighing a feather on a scale buffeted by hurricane winds. Then there's the dark problem. Unlike stars or gas clouds, dark energy doesn't emit, absorb, or reflect light. It's defined by what it doesn't do. Traditional astronomy relies on photons, but here we're chasing shadows that warp spacetime itself. Even gravity waves, our newest cosmic messengers, struggle to help. Dark energy's influence is so uniform that its ripples might be indistinguishable from background noise. It's the ultimate needle in a haystack scenario, except the haystack is the observable universe, and the needle might not even be made of matter. Compounding the frustration is the risk of observational mirages. When studying distant supernova to measure cosmic expansion, tiny errors in brightness measurements, dust interference, instrument calibration can skew results catastrophically. The infamous Hubble tension, where different methods yield conflicting expansion rates, hints at how easily we might be misreading the cosmos's cues. Even cutting-edge labs hunting for dark energy particles face a cosmic catch-22. If these hypothetical entities interact as weakly as theories suggest, spotting them would require detectors the size of planets. The deeper irony, dark energy's omnipresence might be its greatest camouflage. Because it's everywhere, there's no control group in space to compare against, no dark energy-free zone to highlight its effects. It's like trying to study air pressure while trapped in a sealed room. Until we crack quantum gravity or stumble upon a cosmic shortcut like wormholes, our view of this enigma will remain fragmented, a puzzle with half the pieces eternally out of reach. Yet for all the obstacles, the hunt continues, because if there's one thing the universe teaches us, it's that the biggest secrets are always worth chasing. The hunt for dark energy's secrets is accelerating, with a new generation of cosmic detectives gearing up to crack the case. Leading the charge is the European Space Agency's Euclid telescope, a powerhouse designed to map the universe's structure with unprecedented precision. Imagine a cosmic cartographer tracing the invisible threads of dark matter and measuring dark energies push across 10 billion light-years of spacetime. Euclid's razor-sharp infrared eye will capture the shapes and positions of over 1 billion galaxies, hunting for subtle distortions caused by unseen mass and the stretching of voids between cosmic structures. But here's the real game changer. It'll do this in 3D, constructing the largest ever map of the universe's web-like architecture. If dark energy has left fingerprints on this web, like stretching certain patterns or altering how clusters form, Euclid's data could reveal them within this decade. Then there's NASA's Nancy Grace Roman Space Telescope, named after the mother of Hubble. Slated for launch in the mid-2020s, Roman carries a weapon Hubble could only dream of, a field of view 100 times wider than its famous predecessor. This lets it conduct sweeping surveys of the cosmos, tracking billions of galaxies and thousands of supernovae with Hubble-like precision but at warp speed. Roman's secret weapon, its ability to peer back to when the universe was just 2 billion years old, capturing the exact moment dark energy allegedly switched on and began overpowering gravity's pull. By comparing ancient supernovae to modern ones, astronomers hope to catch dark energy red-handed, either confirming its steady nature or exposing dramatic shifts that could point toward wilder theories like quintessence or phantom energy. But telescopes aren't the only players in this cosmic showdown. Deep underground, experiments like the Dark Energy Spectroscopic Instrument (DESI) are taking a radically different approach. Mounted on a telescope in Arizona, DESI doesn't just photograph galaxies, it dissects their light into exquisite detail, measuring subtle redshift patterns across 35 million celestial objects. This lets scientists track how fast different regions of the universe are expanding, searching for inconsistencies that might betray dark energy's true character. Meanwhile, gravitational wave observatories like LISA, the Laser Interferometer Space Antenna, will listen for ripples in spacetime from colliding black holes, offering an entirely independent way to measure cosmic expansion. If these waves arrive distorted or delayed compared to light-based measurements, it could signal that dark energy warps spacetime in ways we've yet to imagine. The most tantalizing wildcard, quantum experiments here on Earth. Labs like CERN and Fermilab are hunting for hypothetical dark energy particles or forces that might interact with ordinary matter under extreme conditions. Picture smashing protons together at nearly light speed, not just to recreate the Big Bang's fury, but to glimpse fleeting anomalies, extra dimensions, unparticles, or even symmetrons that could rewrite physics overnight. While these efforts might seem disconnected from the vastness of space, they're probing the same fundamental question: is dark energy a feature of spacetime itself, or the shadow of something far stranger lurking beyond our current theories? What makes this era so electrifying isn't just the technology, it's the sheer diversity of approaches. From galaxy surveys to atom smashers, each mission offers a unique lens on the mystery, like detectives comparing notes from different crime scenes. If one fails, another might succeed, ensuring that dark energy's secrets won't stay hidden forever. And when the data finally converges, we might not just solve a cosmic riddle, we could uncover truths about reality that rewrite textbooks for generations to come. The countdown has begun. The universe is about to testify. From quantum foam to holographic codes, cosmic strings to shadow universes, the quest to explain dark energy has taken us to the farthest edges of imagination and back. What's astonishing isn't just the sheer creativity of these ideas, but how each one reveals a different facet of our cosmic blind spot. Some theories, like the cosmological constant or quintessence, tweak the known laws of physics just enough to fit the data. Others, like phantom energy or simulated realities, tear up the rulebook entirely, daring us to reconsider what's even possible. And then there are the wild cards: entropic gravity, brane worlds, neutrino-driven expansion. that straddle the line between genius and madness, proving how little we truly understand about the fabric of reality. This isn't failure, it's science in its purest form. Every wrong turn, every dead end is a step closer to the truth. Think of it like a grand cosmic jigsaw puzzle where half the pieces are missing, and we're not even sure what the final picture should look like. The history of physics is littered with ideas that once seemed outrageous: continental drift, black holes, even the Big Bang, until evidence caught up with intuition. Dark energy might be today's enigma, but tomorrow's telescopes, particle colliders, or even serendipitous lab accidents could flip the script overnight. So here's the real takeaway: the universe doesn't owe us easy answers. Its greatest mysteries are puzzles meant to stretch our minds, not just our equations. Maybe dark energy is a quantum fluke, a gravitational echo, or something no one's dreamed up yet. The beauty lies in the hunt, in watching generations of thinkers chip away at the unknown with math, imagination, and sheer stubborn curiosity. Now it's your turn. Which theory grabs you? The elegant simplicity of the cosmological constant, the apocalyptic thrill of the Big Rip, or the mind-bending possibility that we're all just lines of code in a cosmic simulation? Drop your favorite in the comments, because in the end, science isn't a monologue. It's a conversation, and every voice, including yours, adds something vital to the story.